Okay, welcome back to Art of the Day. And for the first time, I have a guest visiting on Art of the Day. Orrin Cohen and I are very old friends. We were like pals in high school many moons ago, and he went on, I don't mean to embarrass you, sir, but he's had a very impressive and accomplished career in infectious disease medicine. He did cancer research. He was part of the first wave of scientists to recognize the HTLV1 retrovirus and then associate that with viral infection in humans. He was in the trenches at New York Hospital at the height of the AIDS pandemic. And later he did his infectious disease fellowship at NIAID and worked in Dr. Fauci's laboratory and office for 10 years. So I thought, who could be a more interesting person to hear from at the moment than my friend Orrin? Thank you so much for joining us, Orrin.
Thanks, Chris. It's great to be with you. It's when you said old high school buddies, old it's all relative, but it was a few moons ago.
I want to share your point of view with people that I know, because I think that scientists and artists have a lot in common. So I'm always interested in conversations between scientists and artists. So, all right, let's just start with something super, super basic for us lay people, regarding the size of a virus. You know, we talked about this before, and you showed me a chart, which I'll probably cut into our conversation about here.
Coronaviruses are about 120 nanometers across, roughly spherical, with some rod-like projections coming off the surface. That's how it's named coronavirus, because under the electron microscope, it's sort of a ball with these spikes sticking out, and it looks like a corona. And so that's 4 millionths of an inch across. And that's roughly the same size as HIV particles and influenza viruses. 4 millionths of an inch, and also very compact. You can think of how much damage HIV does, for example, and the whole genome is 10,000 base pairs, right, as opposed to our 3.2 billion base pairs. And it does everything that it does with about 9 genes. That's what it encodes.
Wow.
And coronaviruses are they have a bit larger genome, so 30,000 base pairs. They encode about 15 genes. So tiny, so compact. And, with a very small number of gene products, they can wreak havoc. It's kind of impressive adversaries.
You were also telling me about the mutational abilities of viruses.
We tend to focus on mutations as bad things. They're scary, they're in movies, they're monsters. And honestly, they are associated with diseases, right? And so we have kind of this negative view of mutations. But overall, mutations are what drive evolution, and very favorable things generally stick with mutations, and that's thanks to evolution is why we're here. Yeah. So viruses replicate way faster, the order of hours. So mutations happen, every cycle that the genome is replicated, and viral enzymes that replicate their genome are not as accurate as humans, for example. So more mistakes happen, more mutations are generated. Most mutations are kind of neutral. They don't, do one thing or another. But under pressure, so viruses, when they encounter our immune system, or if they encounter a therapeutic, a drug, mutations that are happening in the background, ones that allow the virus to continue to replicate in the face of those pressures, will survive. And that becomes the predominant viral strain in that person and then can be transmitted. But in terms of meaningful mutations that, you hear about, more virulent strains or jury's still out. That takes time. That takes very, very careful work. But I would say one thing that makes me a little bit less concerned about viral mutations with this coronavirus is that this virus is transmitted very efficiently. And in fact, it's transmitted before people even are symptomatic, before they even develop fever and cough.
Yeah.
And so this virus does not, in order to continue to be transmitted and keep replicating, it does not need to evade the immune response very much because it'll jump from host to host so fast it doesn't even need to fake the host out.
Artists and scientists share an interest in the fundamental components of things, fundamental components of life and experience. And when, we talked about the nature of viruses, they can outmaneuver human control, though they lack what we perceive to be intelligence. And then later we were talking about the divine wonderment at the level of the physical world where life really starts. And when we were bantering about this, you just made this very interesting remark to me that that these 2 points are interrelated in your mind, and I just wanted to ask you to share some of your thoughts about that.
Yeah, this is a really interesting one, Chris, and it's one that I've thought a lot about over the years, being involved in viral research and immunology research. Viruses, but I mean, you think back on evolution. One thing that's striking is if you look in normal human cells, if you remember from like high school biology, we talked about mitochondria, right? Those are the powerhouse of the cell. That's where energy is generated.
Yeah. And
mitochondria are really weird, right? They are really weird. They're weird looking. They look like bacteria. They look like certain bacteria, actually, and they're around the same size. And they have their own DNA. I mean, for crying out loud. Like, what? Wait a minute. They didn't teach me that in high school, I don't think, but mitochondrial DNA. So it's probable that in the primordial soup, there was once upon a time, eons ago, that a bacterial infection was captured as a symbiont, and evolution then, went forward, and this bacteria became our mitochondria.
Wow.
With its metabolic features. Now, maybe viruses lack that ability. They don't have any metabolism. They can't generate energy, right? And so maybe viruses were just unlucky that they never co-opted an invading thing to generate energy for them. There are several theories about where the hell viruses come from, and nobody knows for sure.
Wow.
But we ascribe to them, we anthropomorphize them when we talk about them all the time. They're ingenious. Mm-hmm. They're smart. Mm-hmm. They evade the immune system. All these purposeful things, right? Of course, they're not even alive, right?
Wow.
And where it really gets a little spooky for me is when you think about this arms race between viruses and our immune responses. Now, our immune system, and this is what really gets me wondering if you want to talk intelligent design. If you want to strip out any overlay from that term, the immune system would be a good thing to think about, because our immune systems have the ability between your antibodies and your T cells to recognize virtually anything that might come in contact, that might invade your body. And when I first learned that, I was like, hang on. What? How can that possibly be? Your body has never seen any of these things. By definition, they're foreign things, right? Yeah. How the hell did our immune system evolve to protect us against foreign threats, right? I mean, a lot of lower life forms have rudimentary kind of, they sense something's invading and there's some non-specific, toxins or whatever. But no, our immune system has the ability to specifically recognize foreign molecules. And the way it does it is that for antibodies, a B cell that produces antibodies has a cassette of genes for antibodies. So an antibody is composed of two long chains called heavy chains and two light chains, which are shorter. And once they're turned into protein, they're linked together with some chemical bonds, and they look kind of like a kid's toy. It has they have this stem that looks like this, and then they have it's almost Y-shaped. It's like a two-tined seafood fork. How's that? Okay. And so the two prongs are the part that recognize foreign antigens, and then the handle of it that's responsible for effector function. So it'll tell a macrophage to gobble this thing up because it's foreign. Get rid of it. Eat it up. But the genes are spliced together, and the way they're spliced together creates an unimaginable diversity of the end product. The permutations of all these splicing events yields about 10 to the 11th. It's like 300 or 400 billion different permutations.
Wow.
And in there is a good fit for almost any conceivable thing that could enter your body. And so
that's crazy to think about. So
we generate antibodies to coronavirus. So that to me, it's the things that cause me extreme levels of wonderment. The developing embryo, how that all happens, how that is all guided by these homeobox genes.
Wow.
And those genes actually are well named. There's like Sonic the Hedgehog is one of the key homeobox genes.
Cool.
So some of them get good names.
Yeah.
But that is quite a mystical thing to watch and to understand. That one of those other parts of life that is it's so unimaginably intricate.
Yeah.
Like you could get the smartest engineers in the world, and you'd be hard pressed to come up with that, right? But that's what evolution has done. And so viruses, the reason the viruses are so smart is because they have evolved. We only know about them because they're able to challenge our immune system to its limits.